In this video, we continue with an example problem of a roller coaster to show you how to apply Newton's law to solve circular motion. So in part A, we found the normal force at point A that the track had to apply to make the roller coaster follow this path. On part B, we get another interesting thing that's common on tests. A lot of times you'll either have the roller coaster underneath, and if you don't make a certain minimum speed, you will fall off. If you go fast enough, you'll stay on the track. Now this is an interesting thing to play with. You can take a platform and some ropes and attach them to the platform, put a glass of water on the platform and swing it fast over your head. And while you're swinging it very fast, the water will not fall out of the cup. And this is not due to a force pushing up on the water. It's due to the fact with the inertia of the water's desire to go in a straight line at constant speed, you have to have the force of the cup to push down on the water to make its turn. Thus the water stays in contact with the cup. It's really the inertia of the water that keeps it in the cup. The problem with it is when you try to slow it down at the very end, if you try to slow it down and your deceleration turns out is too large, then the friction force may not be enough on the cup to the platform, and the platform will slide and fly off. So it's at the stopping and the starting you can lose the cup and the water on the floor, not when you're swinging it over your head. So you should do this outside. In this case, we're on top of the track, and rather than having a minimum speed to make it, there's a maximum speed. And let me show you why maybe that should be. If you're looking at point B, in a given time with a given speed, the ball will move over the coaster, a particular distance, and gravity will cause it to fall. And if gravity tries to fall too far, let's say this far, it'll bump into the track, and the track will push up and keep it on the roller coaster on the track. But if it's going too fast, say the blue line, so that it's out here, and gravity pulls it down only, say, this far, then it is in fact going to follow a path like that and miss the track. So it can't go too far horizontally for the distance it falls, or it won't meet the curvature of the track and it'll fall off. So it's the minimum speed, a maximum speed that'll get you in trouble. So we're looking for this VB max where it just barely leaves the track. That's our problem in step 2. Both types, under the track and over the track, are common. There's also questions about red out, black out, and all sorts of other things on these loop-to-loop type problems. So go look in a Sham's Outline series or other textbooks at the library and get a lot of practice. So let's see if we can find what that maximum speed is for part B. So the maximum speed the coaster can have at point B before leaving the track. Like all other problems, we're going to draw a free body diagram. And as we draw it, one of the things you'll notice that our free body diagram looks the same. Now I'm not going to deal yet with the question of it leaving the track. I'm just going to deal with it being there at point B. So at point B I'd have a normal, and I'd have weight coming down, and I would have an XY axis like this, where I put the Y axis along the radial direction. Then I would attempt to write Newton's second law. Sum of the forces in X is MAX. That says 0 is AX. Again, M was 500 kilograms in this problem from the previous part in the previous video. On the Y direction, the sum of the forces in Y is MAY. Forces include NB minus W is M, and this time I need to put in the acceleration AY. That's my centripetal acceleration, but we need to go back up and look to determine the direction of that. We'll put the formula for the magnitude. That would be its speed, VB squared, over RB, but we need to look for the direction. So let's go back and look at our diagram. In this case, acceleration points downward in the negative y direction, so I need a minus sign. Okay, this is true at any point that it's either touching the track or just touching and starting to leave. When VB equals VB max, NB, the normal force, is equal to 0. And the coaster leaves the track. So the condition for the coaster just to leave the track is the minute when NB goes to 0. Now, if W is too great a negative number for the negative number that's over here, the centripetal force, then NB is positive, pushing up in order to make this work. As the speed gets bigger over here and the centripetal force becomes bigger, making a bigger negative number, it gets closer and closer to W, and the normal force goes down. And at some point, when the speed gets big enough, then it matches the weight, the centripetal force does, and the normal force goes to 0. And anything else than that, we will have an acceleration that will not be equal to weight. And it will turn out that, will not be equal. We'll end up with an acceleration here that is down, but not enough in order to maintain on that track. So it will leave the track. All right, so it will not have, what it will do is it'll just leave off the track kind of like a projectile, tangent to the path. So let's go and work that out. Hopefully my stumbling around there wasn't too bad. We want to make this go to 0. And we want this to be at the max. You might want to just write this as a separate line. So we have minus mg is equal to minus VB max squared over RB times m, and the m's cancel and the minuses cancel, and we get VB max squared is RB times G. There's two roots, one indicating that moves to the positive x, one moving the negative. Doesn't care. This is really speed. So we're taking the positive because we're not looking for. And now let's stop and look at this answer. It says that if the radius of curvature is bigger, you can drive the coaster faster. In fact, if it's infinite, which would be a straight line, then the coaster is not going to leave the track and you can drive as fast as you want. You could build your coaster on Jupiter, have a bigger G, then you could ride it faster. Now there's a problem with that little decision. If you make this G really big, that's great. But Jupiter, of course, is a gas giant, so I don't know how you'd actually put your coaster up there. Not to mention those storms and gases are not good for your materials. If there was no gravity, if this was to go to 0, what would that do? Well, that would say as this went to 0, your speed would have to go down. Now, this may seem strange, but it's not. If there is no gravity, then the coaster is not going to fall, and the track's going to curve away from it, and you're going to leave the track at any speed other than staying still. So, makes total sense. It also has the right units. Meters per second squared times meters is meters squared per second squared. You take the square root, you get meters per second. After we've checked all that and found out, all we need to do is put some numbers in. We go back up and see what was our radius for here. It was 15 meters. Good. We got about 10 times 15 is about 150. Square root of 150, that's like more than 12. If I did that right, we'll see. 15 meters, 9.8 meters per second squared. Punch that in a calculator. .1 meters per second. Alright, this completes this example, and we'll see you on the next video.